Hi everyone, I'm Ovi and my groupmate is Poundip. Thanks Dr. Malik for giving us opportunities to present, and our topic of presentation is lab joint shearing simulation of aluminium, alumina and polyethylene to explore the relationships between the processing, structure, properties and the performance. Now I am going to talk about the outline of our project. We have divided outline in four parts and they are manufacturing, properties, analysis and discussion, and all the details will be discussed in the further section. Now I am going to talk about aluminium fabrication. We all know aluminium fabrication is the process of shaping aluminium into a finished product. We also know aluminium is quick and easy to shape because of its softness and lightness. Metal fabrication can be done in many ways and they are forming, welding, stamping, rolling, machining, powder metallurgy and extruding. So any of them could be used for aluminium fabrication. And then alumina. uh, Alumina is ceramic, so alumina also can be fabricating using different technique. From Callister's book we know there are glass forming process, particulate forming process, cementation, and they all consist of several processes. Pure alpha alumina's melting point is 2400 degrees Celsius. For that reason, the fabrication of such ceramic requires extended calcination of green body, and the temperature should be above 1300 degrees Celsius. It's time to talk about polyethylene fabrication. Some fabrication techniques are compression molding, extrusion, injection molding, and there are two steps in the fabrication of polyethylene. At first stage, linear polymer prepared as a liquid having a low molecular weight, and then curing has been done. And the whole process is shown in this picture. And temperature is set up from 200 degrees Celsius to 250 degrees Celsius, and pressures are 150 to 300 megapascal, and catalysts are pure oxygen and peroxide. Beam additive manufacturing or EBM is very significant thing in our project. EBM is a type of additive manufacturing or 3D printing for metal parts. It is a powder-based fusion process where electron beam is used as the energy source for melting. The powder is spread on the powder bed. Apparently, the metal powder or wire is placed under a vacuum and fused together from heating by an electron beam. Firstly, the metal powder will be loaded into the tank, then it will be preheated. Then to reduce the residual stresses, 700 degrees Celsius is maintained in the chamber. Mainly titanium alloy, mostly fabricated by EBM due to the capability to control low level of interstitial. Then the operating condition of EBM are also discussed here. Now I am going to talk about microstructural analysis and properties of titanium alloy. The titanium alloy is widely used in joint replacement because of its good mechanical properties. And in the figure A, we can see after EBM process done, titanium alloy solidifies into beta grains. Then beta grain boundaries works as nucleation sites for alpha phase. TM images show numerous micro-twins exist inside alpha phase. Strength analysis has also been done for the EBM as cast and rod process. It's been found that at EBM process, the titanium alloy, we have the highest strength. Now I am going to talk about aluminium material modeling. Here we have mentioned the data for elastic modulus, shear modulus and Poisson ratio, and aluminium stress strain curve also considered for aluminium material modeling. And we have get all this data from Abacus example. In this slide, we have done the same thing like the previous slide. This time we have done it for alumina or aluminum oxide. The shear modulus value and elastic modulus value and Poisson ratio are also mentioned, and the stress strain response curve for the alumina is also added here. We are not discussing furthermore because of the time constraint. This slide is for how we did polyethylene modeling. Here we have mentioned the data for elastic modulus, shear modulus and Poisson ratio. Then there is also a stress strain curve also added to analyze the stress strain relationship. Now we are going to discuss about all parts and assembly. In the image we can see the plate and rivet. Plate dimension and titanium rivet dimension is also added. All the drawings are submitted in another file. Now I am going to hand it over to my groupmate Poundip. He'll talk about how simulation has been done and also discuss the results of our project. Thank you.
In this slide, we have followed the shear lap joint simulation from a baker's examples guide, though we have linear time-dependent simulation. We use the same 3D stress elements on the titanium rivet, that is C3D6, and C3D8I is used for the plate. We have given a displacement along the x direction. That is the reason why see in the next slide, in which the simulation video is shown, that the plate moves in the x direction as there is no constraint given to that motion in that particular. So in this slide, I am showing the boundary conditions which represent the lap shear joint simulation. So on the left hand side of this figure, you can see that we are given a fixed boundary condition for the static general step, while we have given a symmetrical condition for the plane symmetry, and on the right hand side there's a displacement along the x direction, of whom the magnitude is given by 2.5. Now we move on to the simulation results for the first material, that is aluminium. And here in the figure we can see that the maximum stress or the failure is indicated near the contact area with the rivet, while a compressive failure is also found at the ends of the plate. While the crack propagation here is limited, the microstructure of the grains are oriented in the direction of deformation during the extrusion process. For alumina 2, the failure is indicated slightly near the contact area of the rivet hole, but the stress isn't that much as compared to aluminium. If we look at figure 7, the microstructure, a low centering process has been used, uh, and the gap among alumina grains can clearly be observed. For polyethylene, failure is indicated again near the rivet contact, but the stress isn't near maximum, and the area away from the rivet contact does not face high stresses. The simulation results for the titanium alloy shows far more promising results for energy absorption. We find plastic strains of more than 55% near the center region, but this is below the failure criteria. It is possible we get a ductile failure if there is a crack present. What really looks promising is the plastic energy absorption curve shown in the extreme right, that is figure 8, and we can see with the dark blue curve there, that shows the dissipation of energy of the rivet. This would make a good lightweight collision absorption structure. Slide, we focus on the processing, structure, properties, and performance for each of the three different materials that we have used. Now, for processing, aluminium is processed by these main processes like casting, CNC machining, forging, and extrusion. While for alumina, powder processing, forming sintering, and heat treatment for hardening are the main processes, and polymerization process and blow molding are generally used for polyethylene. Aluminium structure is FCC, face center cubic structure. Alumina is complex crystalline and polyethylene is simple crystalline structure. While in properties, we can see that aluminium is ductile, having a good thermal and electrical conductivity, while alumina is corrosion resistant, hard and brittle, and polyethylene is light in weight. And there's high strength seen in aluminium, while polyethylene is soft, flexible, and is generally resistant to stress cracking. Here in this slide, we have the processing, structure, properties, and performance summary for the titanium alloy used in this analysis. It can be said that the performance of this alloy is really good, and it is a highly optimized structure, while it is highly ductile and its strength is good, and this is a perfect material as a rivet for a lap shearing process.